Word search, you get a grid of letters and a target string. You may walk orthogonally to adjacent cells, and each cell can be used at most once along the path you are building. In the first example, the board is 3 by 4 and the word is ABCCED, and a valid path exists. Smaller board, letters A through D in a 2 by 2 square. The word ABCD would need 4 distinct steps, but you cannot cover all 4 cells in order without getting stuck, so the correct output is false. We do not treat every cell the same. Depth-first search only makes sense as a continuation of a match. We only start a path where the letter equals the first character of the target. For the word ABCCED, that means we only launch from cells that show A. On this 4 by 4 board, scan for A, each one is a separate entry point before we branch deeper. That is depth-first search on the grid. From a candidate cell we look up, down, left, and right. We pick a neighbor that matches the next letter and go deeper before trying other choices, like a flashlight following one corridor. If this branch fails, we backtrack, undo that step and try another neighbor. Here from the top left A we can step right into B, then continue matching along the word. One rule breaks naive wandering: on a single path each cell may be used at most once. Along the top row we might walk A then B then C. The cell to the left of C is still B, but that B is already on the path. Stepping into it again would reuse a letter illegally. We mark where we have been, often by temporarily blocking the cell, so the search cannot walk in circles. We start with an early exit. If a cell does not match the letter we need at this index, or the step is out of bounds, we return false immediately. We do not waste time exploring dead ends. When we land on a match, we save the character and mask the cell with a hash. That temporary wall stops the search from stepping on its own tail while we build the rest of the word. This is the recursive bloom. From the current cell we ask each neighbor, "Can you finish the word?" The E below matches the next letter, so we recurse into that branch. At the new cell we still need another E. We mask this E and try neighbors. Moving up would revisit the start, but that square is already a hash, not the letter we need, so the collision guard blocks that hop. To the right we find the final E, success. The path from S down to the first E and across to the second E completes the word. Finally, cleanup. As each call returns, we assign board at our C back to temp. The grid is restored so other searches are not blocked by our footprints. M and N are the board dimensions, and L is the length of the word. Time is O of M times N times 3 to the L in the worst case, M times N for trying each cell as a start, and 3 to the L because from each position there are 4 neighbors, but we do not recurse back onto the cell we came from, so at most 3 new branches per step of the word. Space is O of L for the recursion stack. If we keep a visited grid or a copy of the board, that is O of M times N. With in-place hash masking and restore, extra space beyond the stack is constant order 1. Pseudocode for word search. We try depth-first search from every cell. Each DFS step matches one character, masks the cell with a hash, recurses to 4 neighbors, then restores the letter. Outer loop over rows. Inner loop over columns. If a path from this cell completes the word, succeed. No starting cell worked. Recursive helper, match from index K in the word. All letters matched. Off the board, mismatch, or blocked cell. Save the letter before masking. Mark visited so we cannot reuse this cell on this path. Recurse to the 4 neighbors with the next index. Restore the board for other branches. Return whether any neighbor subtree succeeded.